Hello, everyone. Okay, that's a lot of people, and I, I feel pretty nervous. But anyway, uh, welcome. Thanks for coming by. Today, I'm going to tell you a story of how Rust taught me to think about systems. Before we start, I'd like to introduce myself. I am Ravi. I am a full stack developer who loves Rust, Swift, TypeScript, Kubernetes, among other things. And you can find me in GitHub and Twitter in that handle. And if you have trouble pronouncing my name, you could just call me Waffles. Okay. Anyway. Now, and I also run the Rust meetup group in Chennai, and that's partially because I'm a big fan of Rust. The first thing I wanted to answer was why this talk, why I wanted to do this talk. And if you, for that, we need to go through the facts. The first thing is, most of the people love Rust. That's based on the Stack Overflow survey over the past 4 years. And if you visit Twitter or Hacker News or Reddit or whatever, you can find people praising about Rust every now and then, and that's one of the proof. On the other hand, if you see the newcomers, almost all the time they are convincing the compiler that their code is fine. And this is perfectly normal for anyone getting into Rust. I'm pretty sure everyone who tries to compile something in Rust may have encountered this at some point in their Rustacean lifetime. The goal is not to eliminate this problem and write error-free code. Instead, the goal is to understand what those errors mean and how we can get around those errors, just like how we deal with every other compiler. I know that the bar checker could be rather daunting and frustrating for newcomers, particularly for folks from high-level languages. And that's why I present you my story. And it's not just a story. I will be praising Rust every now and then. But I hope that my story helps you to, my story motivates you to try Rust without giving up. For others who are already familiar with Rust, I think this should be fun. It's kind of hard to use this. Okay. Fun at my expense. Anyway, I'll be covering 3 situations. These scenarios are rather common in most of the languages. And whenever I go through any of these situations, I'll be telling you what the borrow checker complained, what the compiler complained, and what those errors meant, what I learned, and how that changed everything. And before I begin, there's one other thing I wanted to say. It's a disclaimer that I will be using some languages in here, and I'm not comparing any of these languages or undermining them in front of Rust. It's just that I've used them because I am familiar with those languages, and I wanted to show you how Rust differs from those languages. Okay, so let's start with variable bindings. So the first example is in Python. It's a snippet. It's somewhat simpler to read, I guess. It's a list of integers, and those are bound to the variable a. And then we are binding a to b. And finally, we are printing the contents of a and b. If we were to write the same thing in Swift, we would do something like that. And both things work. If you run it, you won't encounter any errors, and that's totally normal. But if you do the same thing in Rust, this is perfectly normal, right? You're just declaring a variable, and you're printing the contents. But if you try to compile it, the borrow checker won't allow you to. And that kind of stopped me when I tried Rust for the first time. So I began to read the book. When I tried Rust, Python was my only background. So this is how I thought of memory. So memory is a contiguous set of blocks, and the program requests the operating system, and the operating system gives the blocks to the program, and the program frees them in the end. Now that's partially true, but not exactly. About 4 years back, when the Rust book started, thanks to Steve Klabnik and others in the documentation team, it began with the differentiation of the stack versus heap. And there's this whole new process of thinking through things like you can only have some of the stuff in stack because stack is limited in size. You can only push and pop, and then you can have anything in heap, but then you need to take care of the allocation and deallocation all by yourself. And this changed how I viewed things through the program. When I program. Now, coming back to our example, I'm changing the first element in our list in Python and Swift. And then I'm printing I'm just comparing the results of that change. In Python, I'm using the identity operator, which is the is operator. And in Swift, I'm using the equality operator. The result has got to do with the outcome of this. In Python, you get true. And in Swift, the equality itself is false. And that's because, now I'm curious why, because I just tried that in Python or Swift, and now I don't know why that happened. So I investigated, and I figured out that everything is an object in Python. Everything. That means the A and B, both the variables, are pointing to the same list. And whereas in Swift, it's not the same object. It uses something called copy on write. So when you change B gets a new copy of that list. So the change is reflected in B, not in A. If you have used Rust before, then you would be familiar with cow, clone on write pointer. So that's how Swift works. And if you think about it, these languages take care of these decisions implicitly because they don't trust the programmer, because programmers are known to do bad things like not freeing what they allocate. So the languages take care of the decisions and make the environment, make the program safe. Now I go on figuring out why all the high-level languages do that. And almost all the high-level languages, safe languages, guarantee memory safety through I'm sorry, I missed it. So they are built on the premise that variables can be used any number of times. And this means you only have one or the other way. One way you go for references like Python, or the other way you copy everything like Swift. But references is a bad idea. We know that through C, C++. So we are left with copying. But doing that all the time is also bad, is equally bad. So now we have Ferris coming in and saying, OK, but we can copy some values. For example, integers, pointers, and characters, basically everything that could be in the stack can be copied safely. And what about the other values? More importantly, what about the destructible values, the values of the destructors, which may not be safe for a bitwise copy, and which may need to clean up additional resources, like, say, closing a socket or closing a file or whatever. And these resources may have to move somewhere else in the heap along the way, and we need to keep track of that too. In order to solve this problem, Rust takes some ideas from something called affine types. What this does is that what this says is that a resource can only be used once. And this may sound similar to what the ownership model does. When we use something in Rust, we can only use once. That is, own types can only be used once. And that kind of struck me. when I thought about it, it didn't really mean much, but eventually I kind of got the point. It's a pretty neat way of doing things. And Rust doesn't take in decisions for you. By default, it allocates everything on the stack. And if you want heap, then you need to specify that to Rust. And you do that through two interfaces or marker types, the copy and the clone, which tells you whether the types or values can be easily copied safely, or whether they need additional work to be performed, like heap allocation or file descriptors or whatever. Now, moving on to the next situation, pointers. And pointers are hard in C, at least. When I tried C, that was the only one that scared me away, and I never tried C after that. I couldn't recall all my struggles with the Rust compiler from 3 years back, so let's go for a thought experiment. Let's imagine me as a newcomer rolling my own CSV to JSON converter. The idea is to just read CSV strings through the standard input or whatever and output JSON strings. The rows and columns get translated to JSON arrays. So I start with the search for reading lines from std_in, and the community is kind of great. You always have a highly voted answer in Stack Overflow. And then I go for splitting strings, and I kind of put together my prototype for reading strings from the standard input and outputting them. And I try to compile it, and it doesn't compile because I now see that the collection types, such as vectors, don't implement the display trait. Okay, so I try to implement the display trait, and I regret doing that. And eventually, I ditch my display trait and go for search JSON. Now comes the first borrow checker error. Temporary value dropped while borrowed. Okay, and Rust tells me that and points at the exact line where it happens and asks me to create a let binding for that line. Okay, I do that. And now it compiles. And I couldn't understand a thing, so I researched what had just happened. And I realized that the std_in lock method returns a handle. The handle implements buffRead. And the buffRead gives you the lines iterator, which yields a result of string for every time you call that function, every time you iterate. And the split method that I used creates references on that string. The string gets dropped, and the references get collected into the vector. That's a classic use after free bug. And Rust has stopped us from doing that. Moving on, now I'm kind of familiar with some of the errors in the compiler, and I am having this I'm going for this iterator implementation so that I can do things in a nicer way. So I just call that struct with using it for loop, and I'll get the lines, the JSON lines. And that's easier to work with. So I start from the beginning. I know it returns std_in lock, so I just put it there. And it says missing lifetime specifier. I have no idea what it does, so I search around, and eventually I find that the documentation says something like -a. Now I don't know what that -a is. I'll just put it there. And it says use of undeclared lifetime, and it tells me what change I should make, like changing the struct to use that lifetime. And I had that. Okay. And it compiles again. Now I want to figure out why it works. And that's part of the programming workflow, right? So if it doesn't compile, you shout at the computer. If it does compile, you shout at the computer. And I go on a quest to find what just happened. I see that the std_in struct looks something like that, okay? And the lock method currently looks like that, but Previously, it looked something like that. I mean, about 3 years back. So now the std_in lock, the struct, has its label. But then you see that there's a mutex card, and the label is now in the mutex card. So you follow along, and you find mutex card. Now I see a reference holding that label, and now I finally see it. OK, so references have a label. That's great. Oh, I just missed that slide. Now I realize some things. std_in lock, the struct which we just saw, borrows std_in. And the borrow constrains the owner from moving somewhere else. And that made sense. It made complete sense, because if we are wrapping over a reference, then we cannot outlive that reference, because then we'll have something, we'll have a dangling pointer, which is bad. And Rust has prevented that again. Now I have struggled a bit further after a few more hours or weeks, and I have this iterator. The contents of the iterator doesn't really matter. What matters is that I am not satisfied with that iterator, because the usage looks something like that. I need to deal with an additional square braces, and I need to print the commas by myself, which I don't want to do. So I'm unsatisfied. I'm looking for a way to improve things. And these are all the improvements that I come up with. The iterator should handle everything. Like when I call for line in for every iteration, the line should give me the JSON, the valid JSON output that I should get. I shouldn't have to deal with anything on my own. The iterator should work on all readers. That means a file, it should work. It should work on TCP streams. And writers, same thing. Now I'm kind of, at this point, I'm kind of familiar with the lifetime errors from Rust C, and I kind of like it. So I purposefully go for something like this, a nightmare struct. And now, again, we don't have to focus on the next method. We can just assume that the next method has already been implemented by me, and I don't want to show you my dirty code. The right way to use this method will look something like this. So I have std_in and std_out, and I get a lock on those. So I get handles for both the std_in and std_out, and I use that in the struct. And when I do that, when I use the for each method on that iterator, I get the lines, because it's parsing the std_in and transferring that to std_out, which is exactly what I want. Now I try to make things worse. I'm trying to use a buffer. Okay, buffer in this case is a vector, and the vector implements the right trait, and I'm using the buffer. I'm just passing a reference to that buffer to the struct. That's where our problem is. Instead of passing a mutable reference, that is giving write access, I am giving readable access. It's just a reference. And Rust prevents that. And it's pretty cool, because those are two different types, according to Rust. A readable reference is completely different from a writable reference. OK, so I changed that, and it works. Now, I'm doing something like that. I'm dropping the bytes vector after initializing the iterator. So I'm creating another use after free out of thin air. And Rust prevents that, again. But the borrow checker saves the day. And what about now? I am mutating the vector after creating the iterator. So this means the vector could have reached its capacity at this point and may have relocated elsewhere in the heap. And the pointer is now somewhere else. And Rust doesn't allow me to do that either. So it wouldn't be wrong to say that Rust is like an angel sitting in my computer telling me right from wrong. Moving on, to threads. A ball of fire, threads. We have a concurrency example in Python, and I have a list of values, a list of integers, and it's stored in the variable values. And the do-work function is capturing context from the global scope, and it's incrementing the values 50 times for no reason. I know it's a dumb function, but the point is, just stay with me and we'll see. I'm launching a thread targeting, not just a thread, 20 threads targeting do-work. Keen readers may notice a problem with this step. This is a race condition because when some thread reads the value, some other thread may write the value, and you are overriding an already incremented value. Anyway, we're just assuming that Python helps us, and we're just moving along. I'm starting the threads, I'm joining the threads, and finally I'm printing the value. It's always something like 4,125, 4,699, but never 5,000, because we have lost all those values because of the race condition. If we were to repeat that in Swift, we will be using array. And we have the same do-work function. In Swift, the normal approach is to go for the grand central dispatch instead of threads. So we're using that, and we have a semaphore. We have a dispatch group which acts like a semaphore for us to wait for things, and eventually we will print the value. We will print the sum. It does the same thing, and it has similar results. What about Rust? I have a vector, same 5 elements. I could have used an array because I'm not resizing, but anyway. I have a do-work closure that borrows context from its surroundings, which is the values vector. And I'm spawning 20 threads, again, using that vector, and I'm joining it. Okay, if you know Rust, then you would say that this program is horribly wrong, and I would agree with you, because it doesn't compile. And it says the closure may outlive the current function, which means the vector that we had may get lost because threads, we don't know the lifetime of threads. Different threads could live for different times, and which means if the vector, which is part of this function, gets dropped in the end, then what else is there in the thread? Okay, so Rust asks you to think about your decisions. Like, it asks you, what exactly do you want? Do we want to clone our vector? No, we don't want that. We want writable access from all the threads. So Rust brings you to two elegant solutions to this. The send and sync markers. Send says that passing by value is safe, and sync says that passing by reference is safe. And now there's an endless discovery going on. And I have come up with some realizations. Firstly, we have the normal reference, which applies to a vector or a slice. The problem with this is that the references are bound to the scope, so they're not static. We have vector of some type, and it does implement send, sync, and static, but we don't want to clone or move anywhere, so that's not our choice either. Now we are going for a reference counted pointer, which is static, but then it's not send. It only allows reference methods which use readable reference instead of writable reference. We have refsol, which is send, and it does allow mutable references, but then it's not sync. Eventually, we'll get to the point where we are left with the thread-safe variants of RC and refsol, and that's what we want. And once we change our code, it looks something like that. But again, the only change that you need to worry about is there. Oh, it doesn't highlight. Okay, anyway. This brings us to the question of whether Rust prevents race conditions. No, it doesn't. It only forces you to think about it, because the code is expressive, and that's one other thing I like about Rust. If you read the code, you'll know what exactly you're dealing with. Unlike other languages, Rust doesn't expect you to know things. It teaches you things along the way. Now, coming back to how the last 4 years were for me, I had moments like, why doesn't this work? Or what do you even want from me, Rust C? And I had happier moments like, okay, that is actually great. I didn't know this all this time. And my journey was kind of nice, and I liked every bit of my moment spent with the Rust compiler. So this could probably make you think that isn't Rust hard? Like, isn't Rust too hard to learn? Or if you're a newcomer, then it is definitely hard. But you should stick to it anyway because of the perks that come in the end. Now, if you ask me, isn't Rust too hard to be widely adopted, then I would point you to Steve Klabnik, who says, I believe in people. Thank you, and have a great lunch.